Welcome to this explainer. Today, we're diving straight into pipeline engineering, the dairy preparation sequence. If you're the kind of person who loses sleep over fluid dynamics, CIP protocols, and high-tech industrial automation, well, you are absolutely in the right place. We're exploring the highly automated mechanical processes that seamlessly transform raw, chilled milk into a perfectly standardized product that's fully ready for thermal treatment. Let's get started.
Okay, let's dive into this. Here's our roadmap through the plant's high-tech stainless steel pipeline. We'll start with storage and pipeline control, then move into advanced microscopic filtration, and hit high-speed centrifugal clarification. After that, we'll cover laboratory quality testing, explore automated preparation tanks, and finally wrap up with the pasteurization transition.
All right, kicking things off with Section 1, Storage and Pipeline Control. Picture the sheer immense scale here. Raw, chilled milk leaves these massive storage silos to begin a continuous loop of automated processes, flowing from microscopic filtration to centrifugal clarification and right into the preparation tanks. Now, as engineers, you know sanitary design is literally everything. We're talking highly polished stainless steel pipes that completely prevent biofilm adhesion and ensure total CIP compatibility. Meanwhile, PID controllers meticulously track pressure and flow rates just to maintain that flawless, low mechanical hum of continuous production. But top-tier hardware is really only half the equation, right? The human variable has to be strictly managed too. This spotless, brightly lit food-grade environment is heavily supervised by operators wearing very specific protective gear. We're talking white uniforms, hairnets, gloves, face masks, and safety boots. It's essentially a clean room protocol, making absolutely sure zero biological contamination interfaces with the automated systems they're overseeing. Moving right along to Section 2, Advanced Microscopic Filtration. Now, what's really interesting about this phase is how fluid mechanics meets mechanical separation. The raw milk smoothly enters these robust filter housings, which are precision engineered to mechanically strip away microscopic impurities. And they do it without disrupting the fluid's delicate emulsion stability or increasing the shear stress. Process engineers rely heavily on inline instrumentation here. You've got automated purity sensors and pressure gauges continuously feeding data back to the central PLC so we can instantly detect any pressure drops or filter blinding. That ensures a relentless, perfectly smooth flow.
Next up is Section 3, High-Speed Centrifugal Clarification.
So a centrifugal clarifier is specialized, high-speed rotating equipment that utilizes centrifugal force to mechanically eject unwanted particles. For process engineers, this is physics in its most practical form. We're talking about spinning the fluid at upwards of 6,000 RPMs, creating thousands of Gs of force. Denser particles are violently forced outward and discharged. And PLCs automate these exact discharge cycles to achieve a predictable, continuous cleanliness before the fluid moves even a single inch further down the line. Which brings us to Section 4, Laboratory Quality Testing. So the crucial point here is that even with perfect mechanical design, you still need rigorous chemical verification. Technicians draw samples directly from the line using completely sterile protocols, so outside environmental factors don't skew the data. We use real-time digital analyzers to verify metrics like fat content, protein levels, acidity, and microbiological safety. And this isn't just for keeping records. This instant feedback loop allows engineers to make micro-adjustments upstream, like tweaking the inline fat standardization valves via the PID controller loops to perfectly hit strict regulatory specs.
Let's head into Section 5, Automated Preparation Tanks.
And this brilliantly illustrates what happens once the lab gives approval. The fluid dynamics shift into massive, centralized preparation tanks. This phase requires some truly brilliant system integration. Automated mixers maintain perfect homogenization without inducing shear stress, while temperature sensors ensure that the chilled state holds absolutely steady. Computerized control systems are orchestrating every single valve until the stage-ready indicator lights finally illuminate, confirming the batch is perfectly prepped for thermal processing. Finally, we have Section 6, the pasteurization transition. Let's move to and see how this builds up to the next big step. The prepared milk now enters pasteurization, where heat treatment ensures safety and freshness. Automated valves open up, pumps kick in, and the milk routes directly into massive multi-plate thermal equipment. We are officially shifting from fluid mechanics and mechanical separation straight into advanced thermodynamics. You can almost picture the steam rising around the massive equipment and hear the soft hum of the factory floor as regenerative plate heat exchangers rapidly spike and then drop the milk's temperature. It's a highly unforgiving process, but that thermal precision ensures total microbial safety without destroying the product. Which brings us to a fascinating final thought for this explainer. If this much precision engineering, continuous flow control, and centrifugal physics is required just for the preparation phase, what does it take to truly master pasteurization? It really makes you wonder about the incredibly complex thermodynamic controls waiting in the next crucial stage of production, doesn't it? Thank you so much for joining me on this explainer today. Keep analyzing, keep engineering, and I'll catch you next time.